When we studied the interaction between electric charge and electric field, our goal was to determine the electric field created by point charges or some spatial distribution of charge, and compute the electric field strength representing the field in each point of the space. Now we look at this interaction from the opposite point of view. Our purpose is to examine the force and the torque acting on the point charges or dipoles in a given electric field. For example, if a point-like particle with the charge q and the mass m is placed in an electric field E, then the field exerts a force F on the particle, which is by definition equal to the charge q times the electric field strength E in the position of the particle. The force F will accelerate the particle, and its acceleration A is given by the force F divided by the mass m. If we substitute the expression obtained for the electrostatic force into this equation, we can see that the acceleration is equal to q times E divided by m. Here the acceleration of the particle is directly proportional to the field strength E in the instantaneous position of the particle and its charge, and inversely proportional to its mass. In the study of the motion of charged particles in electric fields, we will neglect the effect of gravity on the moving particle and the back reaction of the charge carrier moving in the electric field, that is the effect of the point charge on the source charges of the field. We neglect the radiation effects as well, which we will study later. Now we will examine the motion of an electron in a homogeneous or uniform electric field. The charge of an electron is equal to minus the elementary charge E, and we denote the mass of the electron by me. In the experiment setup we use two parallel plates with the same but opposite charges where the distance between the plates is much smaller than their size. For such an arrangement the electric field E is uniform in the space between the plates, and points from the positively charged plate towards the negatively charged one. Let us place an electron in a point close to the negatively charged plate. Since the free electron is at rest, its initial velocity v0 is equal to 0. We choose the vertical y-axis such that the electron is at its origin and the axis is oriented upward. The electron experiencing the electrostatic force of the field starts to move in the direction opposite to the electric field, that is towards the positively charged plate. Since the electric field E is uniform, the force acting on the electron is always the same along its trajectory and the acceleration of the electron is constant. Then we can compare the motion of the electron to the free fall of a body under the influence of gravity. The second-order time derivative of the y-coordinate, that is the acceleration A of the electron, is equal to the elementary charge small e times the magnitude capital E of the electric field over the mass me of the electron. Here the minus sign indicates that the acceleration points downward. The integration of this equation gives the first-order time derivative of the y-coordinate, that is the instantaneous velocity v of the electron, and it is equal to the product of the acceleration A and the time t, that is minus small e times capital E over me, times t. If we integrate this equation, we can write the distance y covered by the moving electron as a times t squared over 2, which is equal to minus small e times capital E over 2 times me, times t squared. Since the charge and the mass of an electron are given, the covered distance y, the velocity v, and the acceleration A of the electron in the uniform electric field depend solely on the constant magnitude E of the field strength. If the electron enters in the uniform electric field E with an initial velocity v0 perpendicular to the field lines, then its motion is similar to the one of a projectile moving in the gravitational field. Here we orient the x-axis of the Cartesian coordinate system along the direction of the initial velocity v0. Then the position of the electron in the x direction is given by the initial velocity v0 times the time t, its time derivative is equal to the constant initial velocity v0, and its second-order time derivative vanishes, indicating that the electron has a uniform rectilinear motion in the direction of the x-axis. At the same time, the y-coordinate of the moving charge carrier is still equal to minus small e times capital E over 2 times me, times t squared, with the time derivative minus small e times capital E over me, times t, and the second-order time derivative minus small e times capital E over me, indicating that the electron has a uniformly accelerating motion in the direction of the y-axis. If we eliminate the time t from these two equations, we can express the y-coordinate of the moving electron as minus small e times capital E over 2 times me times v0 squared, times x squared, which is the equation of a parabola. Therefore, the components of the equations of motion in the directions parallel with and perpendicular to the electric field line show that an electron has a horizontal projectile motion, and propagates along a parabola with a horizontal axis in a uniform electric field, provided it has a non-zero initial velocity. If its initial velocity is not perpendicular to the field lines, then we can talk about a general projectile motion, where the parabolic trajectory of the electron is tilted. One of the most famous example for the motion of charge carriers in an electric field is the oil drop experiment conducted by Robert Millikan, in which he measured the elementary electric charge. Millikan studied the motion of electrically charged oil drops under the simultaneous influence of gravity and a uniform electric field. The apparatus used in his experiment is a closed chamber, which we can see in the photo. Inside the chamber, a parallel pair of horizontal metal plates is installed to produce a uniform electric field in the space between the plates, when they are charged with the same but opposed charges. A fine mist of oil droplets is sprayed into the space of the chamber above the plates by an oil atomizer. Due to gravity, the droplets fall, and some of them enter the space between the plates through a small hole in the top plate. When the air between the plates is ionized by a radiation from an X-ray source, the free electrons in the air attach to the falling droplets, making them negatively charged. The experiment starts with the measurement of the velocity v1 of the droplets without electric field. Due to the net effect of gravity and the buoyant force, the falling droplets will accelerate until reaching their terminal velocity, since the drag force representing the air resistance compensates the net effect accelerating the droplets. The net force F of the gravitational and the buoyant forces can be written as the volume V of the droplet times the difference of the density ρ of oil and the density ρ of air, times the gravitational acceleration g. Since the shape of a droplet can be approximated with a sphere, its volume is given by 4 pi over 3 times r cube, where r is the radius of the sphere. This formula can be substituted into the net force, and we obtain 4 pi over 3 times r cube, times ρ oil minus ρ air, times g. Stokes' law determines the drag force acting on the falling droplet, which is equal to 6 pi times the dynamic viscosity eta of the air, times the radius r of the droplet, times the velocity v1 of the droplet. For a droplet moving with the constant speed v1, the balance equation of the forces states that the magnitude of the net force of the gravitational and the buoyant forces is equal to the magnitude of the drag force. In the second step of the experiment, the velocity v2 of the droplets is measured in the uniform electric field between the charged plates. By adjusting the electric field strength, the speed of the charged droplets moving in the field can be increased or decreased. Then the magnitude of the field can be modified until the given droplet is suspended in mechanical equilibrium, indicating that the electric force, the net effect of the gravity and the buoyant force, and the drag force are in balance. Here the electric force exerted on the droplet is given by the charge Q of the droplet times the electric field strength E. The magnitude of the electric field can even be raised so that the droplet starts to move upward, and then reduced to its balance value. As a result, the forces acting on the droplet are in balance again, and the droplet has a uniform linear motion with a constant speed v2. Then the balance equation for the magnitudes of the forces states that the electric force Q times E minus is equal to the net force of the gravitational and the buoyant forces, plus the drag force acting on the droplet at the speed of v2. If we substitute the net force from the first balance equation into the second one, we can write that Q times E is equal to the sum of the drag forces acting on the droplet when it has the speed v1 and v2. By applying Stokes' law, we can express the charge Q as 6 pi times eta times r over E, times the sum of the v1 and v2. As a result, for a given magnitude E of the electric field, the charge of the droplet is determined by its radius r and the velocities v1 and v2 measured in the experiment. The radius r can simply be determined from the first balance equation, since r squared is given by 9 times eta times v1 over 2 times g times the difference of ρ oil and ρ air. If the densities of oil and air, the viscosity of air and the gravitational acceleration are known, the charge Q could be determined by measuring the velocities v1 and v2 of a droplet for a given electric field strength E. Millikan performed a series of measurements in his experiment, and he found that the values of the charge Q attained by the individual droplets are always an integer number multiples of the elementary charge E, which is equal to 1.6021 times 10 to minus 19 coulomb. The relative error of the experiment was only 0.6% due to the error in the viscosity of air, which was corrected later. We note that Helmholtz already recognized that Faraday's laws of electrolysis have an important consequence. If matter consists of atoms, then charge has necessarily a quantum nature. There must exist an elementary charge, and any macroscopic charge is an integer multiples of this elementary charge. Helmholtz also determined its value as the ratio of Faraday constant to Avogadro's number. However, this ratio gives the average value of the charges of many ions, whereas the oil drop experiment determined the charge of individual ions. After examining the force exerted on a point charge or a charge carrier by an electrostatic field, we will turn to the study of dipoles and electric fields. Let us place an electric dipole in a uniform electric field, where phi is the angle between its dipole moment p and the electric field strength E. Then the forces F and minus F acting on the individual charges plus Q and minus Q of the electric dipole have the same magnitude and opposite direction separated by a perpendicular distance d times sine phi. This pair of forces makes a couple. As usual, D is also represented by a vector pointing from the charge minus Q to the charge plus Q. The electrostatic forces F and minus F are given by Q times E, and minus Q times E. The couple has a turning effect on the dipole about an axis of the dipole perpendicular to the plane of the forces. This turning effect is the moment of the couple or the torque tau with regard to its rotation axis, and it is given by the cross product of the distance vector d and the electrostatic force F. Then the torque tau can be written as the vector product of d and Q times E, or the vector product of Q times d and E. But Q times d is just the dipole moment p, and we can conclude that the torque tau acting on a dipole in a uniform electric field is given by the cross product of the dipole moment p and the field strength E of the electric field. We can write the magnitude of tau as the product of the magnitudes of p and E, times the sine of the angle phi measured between them, and the torque is perpendicular to the plane spanned by the dipole moment and the electric field strength. As already mentioned, the torque represents a turning effect, and it attempts to twist the dipole in the direction of the electric field. We also see that the net force of the couple acting on the dipole is zero, that is, the center of the dipole has no acceleration. We can study this effect with an insulating rod with a small metal sphere attached to both ends, which can spin around its midpoint. If we charge the metal spheres with the same but opposite charges and place the apparatus in a uniform electric field E, then it behaves as a dipole in the electrostatic field. The torque attempts to align the dipole to the straight field lines, but at the same time the body starts to oscillate about its rotation axis due to the inertia of the system of the rod and the spheres. Newton's second law of rotation can be applied here, which states that the torque acting on a rigid body about a fixed axis is equal to its moment of inertia, times the angular acceleration. Then the moment of inertia I times the second order derivative of phi with respect to the time is equal to minus the product of the magnitudes of the dipole moment p and the electric field E, times sine phi. The minus sign indicates that the torque tries to restore the direction of the dipole aligned to the electric field. Since we talk about an oscillation with a small amplitude, that is, the angle phi is small, we can approximate the sign of phi with phi in the first order. Then we can write that I times phi double dot is equal to minus p times E times phi, or phi double dot is equal to minus omega squared times phi, where omega square is defined as the ratio of p times E to I. The solution of this differential equation is the rotation angle phi as a function of the time t, which is equal to an amplitude c of the oscillation, times the sine of omega times t. The amplitude c is a constant of integration which can be determined by the initial value condition, that is, the initial direction of the dipole with respect to the electric field. The solution shows that the system of the rod and the charged spheres performs a small oscillation in the uniform electric field with the angular frequency omega. We can also give the period t of the harmonic motion of the dipole in the electric field defined as 2 pi over omega, which is equal to 2 pi times the square root of the ratio of I to p times E. The greater the electric field and the dipole moment are and the smaller the moment of inertia is, the greater the frequency of the oscillation or the smaller its period is. Electric dipoles have a potential energy in an electric field, and the definition of the potential energy of a dipole placed in a uniform electric field is very simple. Let us consider a dipole with the dipole moment p in a uniform electric field E, where the angle between the dipole moment and the direction of the field is equal to phi null. The potential energy of the dipole is determined by the work that any external force needs to do on the dipole to change its direction in the electric field. We can compute the work W by integrating the magnitude of the torque tau acting on the dipole with respect to the angle from phi null to phi. Since the torque tau is given by the cross product of the dipole moment and the electric field strength, we have p times E times the integral of sine phi with respect to phi from phi 0 to phi. By performing the integration, we obtain p times E times the difference of cosine phi null and cosine phi. We are interested only in the change in the potential energy and we fix the initial orientation angle. If we set phi null to 90 degrees or pi over 2 given in radian, then the cosine of phi null vanishes. As a result, we can define the potential energy as the work done on the dipole by the electric field turning the dipole from the inclination angle of pi over 2 to the angle phi. That is the work W, called the potential energy U, is equal to minus p times E times cosine phi. Since phi is the angle between the vectors p and E, we conclude that the potential energy U of an dipole with the dipole moment P in a uniform electric field E is given by minus the scalar product of the dipole moment P and the electric field strength E. If the direction of the dipole is perpendicular to the field lines of the uniform electric field, that is the direction angle of the dipole moment P is equal to pi over 2, then the scalar product vanishes and the potential energy of the dipole is equal to 0. If the dipole moment P and the electric field strength E point in the opposite directions, that is phi is equal to pi, the potential energy U of the dipole has the maximum value, which is P times E. If the dipole pointing in the direction of the electric field strength has the minimum potential energy, given by minus P times E. In that point the dipole is in a stable equilibrium, and any small change in the direction of the dipole results in a torque turning back it to its direction parallel with the field. Therefore the angle 0 represents the minimum of a potential well of the dipole in the electric field, indicating that the dipole is aligned with the electric field lines. If we rotate the dipole against the torque exerted on the dipole by the field, we increase its potential energy till its dipole moment points in the opposite direction to the field. In that direction the dipole reaches its maximum potential energy where it has an unstable equilibrium. For any small change in the direction of the dipole the torque twists the dipole from its anti-parallel position to the parallel one, pushing it towards the bottom of the potential well. Now we consider a more general case where we study the effect of an inhomogeneous electric field on a dipole. In an inhomogeneous electric field E, the magnitude and the direction of the electric field strength depends on the position. If an electric dipole with a pair of point charges plus Q and minus Q is in the electric field E, then the magnitude of the electrostatic force F sub plus acting on the charge plus Q and the force F sub minus acting on the charge minus Q are not necessarily equal. If the position vector points from the reference point O to the charge minus Q of the dipole, then the force pair acting on the dipole is the following. The force F sub plus is equal to the charge Q times the electric field strength E in the point given by the vector sum of the position vector R and the displacement vector D, whereas the force F sub minus is equal to the charge minus Q times the electric field strength E in the point determined by the position vector R. As a result, the net force F acting on the dipole is given by the vector sum of F sub plus and F sub minus, that is Q times E evaluated at R plus D, minus E evaluated at R. The first term in the square brackets can be approximated with its Taylor expansion around the point R in the first order, which gives Q times E evaluated at R, plus the directional derivative of E along with the displacement vector D evaluated at R, minus E evaluated at R. If we assume that the distance D between the charges plus Q and minus Q is small compared to distances over which the field varies, the limit of the ratio or the change of rate of the electric field strength will approximate the right-hand side as the distance D approaches 0. Then the net force F is equal to Q times the directional derivative of the vector field E along the displacement vector D. Since the dipole moment P is equal to Q times the vector D, the net force F acting on the dipole with the dipole moment P in an inhomogeneous electric field is given by the directional derivative of the electric field strength E along the dipole moment P. In the Cartesian coordinate system the ith component of the force F is equal to px times the partial derivative of the ith component with E with respect to x, plus py times the partial derivative of the ith component with E with respect to y, plus pz times the partial derivative of the ith component with E with respect to z. Here the index I represents the Cartesian coordinate components of the vectors F and E. If we place an electrically neutral conductor in an electric field, then it becomes a dipole due to the separation of charges. Therefore, the effects of the electric field on the conductor can be explained by applying these simple cases presented here. In a uniform electric field a torque tries to turn a metal rod until its longitudinal axis is parallel with the field lines. As soon as the rod is aligned with the uniform electric field the torque acting on it vanishes. In another example we charge a glass rod by rubbing it with leather, and an electrically neutral sphere becomes a dipole due to the separation of charge in the electric field of the charged glass rod. The inhomogeneous electric field of the rod will attract the sphere since the field exerts a force on the dipole in the direction of the increasing field.